Number 4 is a very fun, challenging problem, and I really think, again, it follows the same routine as what we saw in number 2, where all we got to do is draw 3 force diagrams, and from those 3 force diagrams, you will be on your way to solve this. So, first things first, I'm going to say my first force diagram will be the 5 kilogram box, my second force diagram is the 10 kilogram box, and what we will look at is a system of both the 10 and the 5 kilogram box. So in this situation, you will notice that the 5 kilogram box, first off, because I believe this is set up on a frictionless surface, in a frictionless surface, that means that piece is frictionless. What you will notice is that this whole system will have to be accelerating to the left, because if you push a box on a frictionless surface, it's going to accelerate. We know that. So that means the 10 kilogram box would have to go. The 5 kilogram box would also have to move as well and accelerate to the left. So if I drew in a force diagram, we would have Fg on the 5 by Earth. We would have an Fn on the 5 kilogram box by the 10 kilogram box. So that's a very important force, because once I write that out, I probably know that there's going to be a force pair somewhere in there. The other situation that you realize is, oh wait, shoot, there has to be a force going to the left. And the only way to explain this is actually talking about FFS. And you wonder, why is it static? It is because this box is not moving in correspondence to the 10 kilogram box. They are moving as one. So it's actually a static coefficient, or a static force there on the 5 kilogram box by the 10 kilogram box again. So that is a static, but it is a frictional force nonetheless that would actually be pushing it forward. They are not moving in terms of each other, so that's why it's again static. We know that those two forces would be equal. 10 kilogram box is kind of crazy. We have an Fg going down. We also, this is the one that throws a lot of people off, there is an Fn on the 10 kilogram box by the 5 kilogram box. Why? Because, well, if you think about being the 10 kilogram box, you're being pushed up by the floor, you're going to be pushed down by the 5 kilogram box, as well as gravity. I am sick of moving on over here. So those are the two pieces there. You have an Fn on the floor going up on the 10 kilogram box by floor. And of course we have a 30 Newton force going this way, Fn on the 10 kilogram box by, what is it in this situation? By the hand. And what is also really weird, this is why this problem can be kind of difficult to understand. Notice this frictional force right here. Well, because the 10 kilogram box has to push the 5 kilogram box forward, what does the 5 kilogram box do to the 10 kilogram box? It pushes it back. It is again that FFS on the 10 kilogram box by the 5 kilogram box. And the only way that I can describe this in order for people to really get a good understanding is, again, think about these surfaces. They are rough surfaces. So this is the picture that I want to have in your heads. Again, this is the 5 kilogram box. This is the 10 kilogram box. As this pushes this guy forward, so if you think about these things running into each other, pushing that guy forward, what is this box doing? This box is actually pushing that box backwards. So you notice that this FFS is, again, if we want to start making things equal to each other, this piece right here is equal to that piece right there. It is another force pair. There's two of them in this situation. The other force pair is being this Fn right down here. So we have this force pair here, and we have that force pair right here. So that is our situation. You notice that those are really kind of messy force diagrams. The one that makes this really easy is if you draw a force diagram for both of them. Again, you start to notice that this is always the way to go. You have our Fg on the entire system on the 10 kilogram and the 5 kilogram by Earth. You'll notice that we can combine both of those because Fg's are both pulling downward. We have Fn on our system by the floor. So the floor has to hold both of those suckers up. And you'll notice the frictional forces cancel out, and all we're left with is that, whoa, it's a long force arrow, that 30 Newton force Fn on the 10 kilogram. Or, yeah, it's actually on the 10 kilogram, but it's also the thing that's causing both of them to move by the hand. And when I look at this force diagram on over here, you start to realize life gets really simple for you. Because we know that that's 30 newtons, and you can solve for the acceleration really easy. So net force, let's go back to our equation. A equals net force, the mass of the system. The system that I am using is this force diagram. Why am I using this force diagram? Because I know basically everything that I need to know in this situation. This mass of the system is 15 kilograms. Acceleration is what we're trying to solve for, and the net force is 30. And so when you solve this, you're going to get 2 meters per second squared. Technically, that would be a negative 30 because it's going to the left. So it would be negative 2 meters per second squared. So that would be our acceleration in our first piece. The next piece that it's asking, what is the force of static friction between the top and bottom block? That is referring to that guy right there. And so now all what I do is I say, well, now I know the acceleration. Let's go use that here again. A is equal to net force times the mass of my system. What is my mass of my system in this case? It's the 5 kilogram box. 5 kilogram goes down there. Negative 2 goes in over there. And you'll notice that the net force in this situation, look at what the net force is. It is just negative FFS because it's going to the left. So again, if we solve this, we get negative 10 equals newtons equals our negative FFS, which means that FFS must be equal to 10 newtons. A good test to see if you really understand this is to try to solve for the FFS on over here without knowing that it's 10 newtons. So it means use this force diagram to see if you can solve for it, and you should be able to. And the last question, I believe, is part C. What is the minimum coefficient of static friction necessary to keep the top block from slipping on the bottom block? What you would have to do in this situation is, in this, again, we got FFS as being 10 newtons. We're looking for the coefficient. Remember, coefficient of static friction times Fn. And this is the Fn that's causing the friction. So if we go on over here, you'll notice that that's referring to that force, which is equal to Fg in this situation. So all we got to do is set the 10 newtons equal to mu sub s times the Fg, which is 9.8 newtons per kilogram, times the mass of, well, what is the current cause of the Fg? Current cause of the Fg is this 5 kilogram box here, so we just go 5 kilograms there, and you would solve for mu s that way, and you'd get your answer. So that is number 4. Number 4 is kind of difficult, but you'll notice, again, once you get these force diagrams, you're pretty much good to go. And you'll notice that this force diagram really always helps you out to get your acceleration. So that is problem number 4. If you have any questions, again, feel free to send me an email.